Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So good morning, students. So we are going to start this new chapter, the S block elements. So if you talk about the S block, then you must understand what is the S block in the periodic table. And S block, this is the two groups that belong to the S block. The first two groups of the periodic table, they belong to S block. And why they belong to S block? Because when you write the electronic configuration of any elements in these two groups, the last electron will go to the S subset. And that is why we divide this periodic table and in different blocks. So this is the S block. Since S orbital contains only 2 electrons, so we have only 2 groups in the S block. And the P block, then comes the P block. P block comes here, and P block has 6 different groups. You go the P block or the P orbitals can contain 6 electrons. 3 orbitals are there, and each orbital can contain a maximum 2 electrons because of the Hund's rule. So that is how what we get. The 6 electrons can be in the P orbitals, and so there are 6 different groups for the P block. So this is P block, and then we get D block, and this is the F block. The last electron enters the F orbitals, and so the 14 elements will be there in D block. 10 different groups are there. So that is how we get. So the first group and the second group. Initially, it was also called 1A and 2A. Now people call group 1 and group 2. So the electrons present in an atom occupy various suborbitals of available energy levels in the order of increasing energy, and that is what we call the Aufbau principle. And according to Aufbau principle, we put electrons in different suborbitals while writing the electronic configuration. The last electron of an atom may find itself in either of S, P, D, or F subcells. So whenever while writing whatever the last electron while you are putting, whether you are putting it in S, P, D, or F subcells, based on that, to which block this element will belong, for which you are writing electronic configuration, which is called the block, or the S block, P block, or D block, or F block. So the elements of the atom having their last valence electron gone in the S suborbital or S subcell are called S block elements. And so these S block elements are only these first two blocks. So all as the S orbitals can accommodate only 2 electrons, as I said, S orbital can accommodate only 2 electrons because it has only 1 orbital, and 1 orbital can have maximum 2 electrons only. So since S orbitals can contain maximum 2 electrons, so there will be 2 different groups. If there is only 1 electron in one group, all the elements having 1 electron in the S orbital, they belong to one group, the first group, and all the elements having 2 electrons in their S orbital, outermost S orbital, they belong to the second group. And so this is what we get, the alkali metal groups and alkaline earth metal groups. So the S block elements having only 1 electron in their S orbital are called alkali metals. So this is the group of alkali metals. And so how many elements are there? 6 elements are there: lithium, sodium, potassium, rubidium, cesium, francium. So francium is radioactive. Its half-life period is very small. It's very radioactive, readily radiates alpha beta particles. And so these other elements up to the cesium, they are stable, they have a stable nuclei. So usually when we study the chemistry, we usually study the chemistry of lithium to cesium only. Francium, since it is radioactive, it is important there for the radioactive purposes. It is not for the chemistry, or we don't study chemistry of francium because it is radioactive. Who will go and study its chemistry? The chemistry of radioactive elements are also being studied, but that is mostly for the academic purposes, that does not have any use in the chemical processes. And then second group that belongs to the alkaline earth metals, they are called alkaline earth metals. The beryllium, magnesium, calcium, strontium, barium, and the radium. It's again the radioactive. So these elements you should remember: lithium, sodium, potassium, rubidium, cesium, beryllium, magnesium, calcium, strontium, barium. This is beryllium, this is barium. You should not get confused. Beryllium and barium. And this is Francium, strontium. Sometimes some students get replace their position. So this is francium, it belongs to first group. Strontium, it belongs to the second group, alkaline earth metals. These all these metals, they have one electrons in their outermost shell, and all these metals, they are all metals. They are all these elements having two electrons in their outermost shell. So the electronic configuration of this cell will be, this group will be NH1 outermost shell, and for this it will be NH2. So the S block elements having only one electron in their s orbital are called alkali metals, and they belong to group 1. We have just seen the S block elements having two electrons filling their outermost s orbital belong to group 2, and they are called alkaline earth metals. There are certain properties which are quite general, which belongs to both the both group elements. So those properties let us see. The general properties of S block elements, and the general properties means they are all metals. I am saying something which will belong to all the both the group metals, means all the S block metals. So they are all metals, and we know, as I have said, they are all metals. And why they are metals? Because they have only one or two electrons, and they can easily give those electrons. So they are electropositive, and these electrons, which are 1 and 2, they are actually many electrons found in the conduction band. They behave as a free electrons, and because they are behave as a free electrons, they can behave as a conductor, metallic conductor, because free electrons are now available to move in the conduction band to conduct electricity. And what is the valence and conduction band? So a little bit I have explained in the chemical bonding chapter. If you want to study it in more details, you can go and see any physics books, because it is more better described in the physics book, because this band theory has actually more explained in the physics of some semiconductor devices when we study there. So all of the S block elements, they are metals. So remember, they are all metals. And if you look at the periodic table, all the S block elements, they are metal. All the D block elements, they are metal. All the P block elements are metals. And if you just draw a diagonal line from here to here, all the elements which belong to this region, heavier mostly, they also are metal. Only the elements which belong to this diagonal, it will start with the boron and astatine somewhere. And so they are all metalloid, and the elements which come on the upper portion of the P block, they are mostly non-metals. So the very few elements are non-metallic, and most of the elements are metal. Most of the elements that we know and they are part of the periodic table are metals that we know. Now, so in general, they are shiny. They're shiny, silvery, good conductors of heat and electricity, because they are metals, good conductors of heat and electricity, and they lost their valence electrons very easily, because those valence electrons are loosely bound. And why they are loosely bound? Because the effective nuclear charge is weak in the case of alkali and alkaline earth metals. Effective nuclear charge. What is that effective nuclear charge? The effective attraction outermost electron that experience because of the positive charge, the presence of protons in the nucleus. And why the an element or an atom can have n number of protons, but effectively all those protons, their force is not experienced by the electrons, because there are many electrons as well between nucleus and outermost shell electrons, and the electrons, they repel each other. So whatever the intervening electrons are there, they will also be repelling outermost shell electron. So one attraction force the outermost electron gets because of the nucleus, but it also experiences certain repulsive force. Whatever the net force that they experience, that is we call effective nuclear charge. The net nuclear charge is because of the how many electrons are there, and effective nuclear charge effectively attracts of how many protons it is experiencing. It is, suppose if it is a sodium which has 11 protons, so it is the electrons in the 3s1, it experiences attraction of all the 11 protons, and it experiences attraction of only net attraction of 1 or 2, whatever the number of protons, that we call effective nuclear charge. So they can easily lose their electrons, because the effective nuclear charge on the outermost shell is very weak, and that attraction is weak, so they can easily be promoted. Their electrons can easily be kicked out. So they have low electronegativity. Again, low electronegativity, mostly electronegativity actually with the term we define in the covalent bond. When the covalent bonds are there, so the shared pair electrons moves to which side, which side its delocalization is favor, whether which side it is shifted, or if you talk about the electron density, which side the electron density is polarized. That is electronegativity, and that we define in the covalent uh, compounds. And because of the Fazan's rule, we also know most of the ionic compounds, they also have a covalent characters. And that covalent character, so there, if the covalent character is there, so we talk about the electronegativity, and they have very low electronegativity. Again, the reason if the element is having high electronegativity, it is because the effective nuclear charge is very high for that element. The outermost shell electron effective nuclear charge is very high. So if that nucleus is attracting its outermost shell electron, so it can also attract more strongly to the electrons that it gets in the sharing from other elements. So that is how the effective nuclear charge is more, electronegativity is more. So because the effective nuclear charge in the case of S block elements is low, so their electronegativity is also low. So they form basic oxides and basic hydroxides. So their oxides and hydroxides are basic, means if you dissolve them, they react with acids. So that is why they are called basic hydroxides. They do not react with the bases, they will only react with acids. So they form ionic bond with fixed oxidation states. They also form ionic bonds usually because they can easily lose their electrons, and if someone is there to accept it, so that will be anionic, and so there will be cation anion interaction, which is what called the ionic bond. And they have characteristics flame color, and this we will study in details. Characteristics flame color means if you heat any alkali and alkaline metal and they are loosely bound electron, the valence shell electron, it will excite, it will go to the higher state, and once it reverts back, it imparts certain color, and that color we call the characteristic flame color. So we have to heat that metal to a certain energy, we have to provide certain energy, and that because of that it will go to higher electronic state. Higher electronic state means the electron is excited to higher states, higher subcells or higher energy levels, and usually higher energy levels, higher cells. And so, and because that state is not the stable state, because the electron has gone to higher state, it has absorbed certain energy, and once it has absorbed certain energy, the energy of the entire system has gone down, and which is not a stable condition. So it will, the electrons will go back and it release whatever the energy it has absorbed, and so that energy has it is in the visible range, so it imparts certain color, and that color we see, and that is why they have characteristic flame color, because that energy that these electrons they release when they come back to the ground state, that belongs to the visible light or visible range, and this electromagnetic spectrum that you see certain radiation, it belongs to the visible color. So alkali metals, let us look about now the general characteristics we have seen of the S block. Let us now look into the two groups one by one. First, alkali metals, the first group. So the group 1 of the periodic table contains 6 elements, and that I have named earlier: lithium, sodium, potassium, rubidium, cesium, and francium. All these elements are typical metals. Francium is radioactive with longest lived isotope with a half-life period of only 21 minutes. So longest lived isotope of francium is 223, francium 223. It only lives for 21 minutes. It means the nucleus is very unstable. You can have it, you can form it artificially or maybe during a nuclear reaction for a certain period of time, but it will not be stable. It will emit particles and will form some other element. These elements are usually referred to as alkali metals. Why they are referred to as alkali metals? Because they form hydroxides on reaction with water, which are strong bases or alkalis. So hydroxides of alkali metals, they are actually basic. So OH minus, they furnish OH minus ions, and these hydroxides are called alkalis or bases, and if they are called alkalis, that is why these metals are called alkali metals, because the hydroxides form alkali. That hydroxide is an alkali, a base. And how this hydroxide is formed? So it reacts, these alkali metals react with water so vigorously. You should never try this. So it reacts so vigorously, it actually catches a flame. So and it forms hydroxide. So to the loose held S electrons in the outermost shell, So the loosely held s electrons in the outermost shell makes them the most electropositive metal. So as I said, the electrons, the outermost shell electron is loosely bound because of the weaker effective nuclear charge and so with weaker nuclear attraction, so the electrons can easily be removed, and so they usually form cations very easily. They form cations and they are electropositive metals. They have electropositive character because they can easily become positive. They can easily form cations, and so they are electropositive in nature. And if you look at their electronic configuration, so lithium, sodium, potassium, rubidium, cesium. So let us start with the lithium. Lithium, we know what is the its atomic number. It is 3. So what we write, 1s2 and then 2s1 according to above principle. Then sodium, 1s2, 2s2, 2p6, 3s1. So this 1s2 is what? It's electronic configuration of helium. So the electronic configuration of lithium can always be written as helium, then 2s1. This is how a general trend that people also follow. And the sodium, for sodium, 1s2, 2s2, 2p6, 3s1. And here 1s2, 2s2, 2p6. This is the electronic configuration of neon. So we can write up to here neon and then 3s1. Then potassium has sodium has 11 electrons, potassium has 19 electrons. So you can do potassium 1s2 up to the where the 19 electrons are filled totally, and you see the last electron in all the cases that we have seen so far, it goes to s orbital. So this all these elements belong to s block, and they all have one electrons in the outermost shell, and you see one electrons in the outermost shell. So they are part of the first group. And so why their periodicity in the property is there? Because the electronic outermost shell electronic configuration is being same, and it is coming periodically. After certain time it is found to be same. So certain other properties are also have they are also similar or same for these group elements. And this is how the periodicity in property we see, because of the same repetition of the similar outermost shell electronic configuration. And then rubidium again we see, and here the d electrons also come into the play because 3d orbitals are now available after the potassium, and 3d orbitals are now available. So 10 electrons will go also to the 3d orbitals, and now what we get, the krypton, and krypton 5s1 electronic configuration. This up to here 4p6 is the electronic configuration of krypton, and so after that by 5s1 1 electron. So this is the electronic configuration of rubidium that we get. So what you have to remember, you have to remember the krypton. After krypton it is the rubidium. After argon, what is the sodium? After neon, what is, sorry, after argon it is potassium. After neon, what is sodium? After helium it is lithium. All these elements that you know, they are noble gases. They belong to noble gas family, or the, yeah. Now the cesium, in the case of cesium, we see its electronic configuration. If you write according to above principle, we come here 5p6 and 6s1. Up to here 5p6, what we call its electronic configuration of xenon, which is also also a noble gas. And so then 6s1, this 6s1. So why we get the electronic configuration. This is also the electronic configuration. So only, and francium, with francium we write, which goes to electronic configuration of a radon up to here, and then 7s1, 7. So what we get, the electronic configuration, similar electronic configuration of all the metals, means one, the electronic configuration of one noble gas and one s electron in the outermost shell. This is what we get for all the alkali metals. And what overall we have observed is only one valence electron is there. So outermost shell has only one electron. So this is 7. For out cell, 7th cell is the outermost cell. You can see there is no orbital of the 7th cell other than 7s1. This, there is no orbital of 6th cell other than 6s. So this is how their outermost shell contain only one electron, and all these electrons are loosely bound. And because they are loosely bound, they can easily be donated. They can easily be given out. They can easily be lost. And so it will form monocation, monovalent cation, or M plus ion, M plus ion. So this, and M plus ion means its oxidation state is +1. And because they can easily form cation and they are so vigorously lose electrons, so they never found they are very reactive, and because they are very reactive, they never found in free states in the nature, particularly on the earth. So they are never found, they are always found in their as their compound. So we know NaCl, N sodium source is NaCl. The salt, rock salt that we get, and the ocean contains NaCl, large amount of NaCl. The potassium, KCl, there are many, since their oxides are also there that exist in the nature, but they never found in the free state because they are highly reactive. And why they are highly reactive? Because their electrons are loosely bound and they can easily donate them. So let us look at the alkali metals and their ores. And their ores means their natural source, in which form they occur naturally, and from where we can extract these metals, which are called ores. Means their percentage and their extraction from the natural sources is easy. Then we call such natural resources as ores. So the lithium, we can see that they are all light silvery in color, and this is lithium, so it's light darker, but it's silvery. And this you can see, this is more bright and more silver, and the rubidium, cesium, they have more luster. And this is a sodium. Sodium you might use in making sodium fusion extract when you will go to organic chemistry laboratory, and particularly in class 12. And when you have you will be given a certain organic compound to find out whether this organic compound contains any halide or not. So what do? You add a small amount of sodium metal and that organic compound, that sample whatever is given, then you heat them together. And while heating them in the water, what will you get? The sodium fusion extract. If the halide is there, so halide will come as, means halide means fluoride, chloride, bromide, iodide. When if it is there, so it will form, it will go into the solution, and like NaF, NaCl, so NaX will be there in the solution, and the iodide, it will form only when iodide or halide, when the sodium metal is there, because the electron that they need, they will get from the sodium metal. And so there is certain taste of the halides, and with that we can detect whether halide is there in that organic compound or not. So sodium we use, and you might use this, and sodium is not, these metals are usually not kept in the open air because they can easily react with oxygen. They are actually put in the kerosene. So they are being put into the kerosene, and we use that, and in a spatula a small amount we cut just for a small period of time, and then immediately we use it to make sodium fusion extract. So the alkali metals and their ores, the lithium, the ores of lithium is the lepidolite. Lepidolite, it contains lithium, it also contains potassium, rubidium, and some amount of cesium as well. There are other metals as well. So lepidolite is the ore of lithium. And then spodumene. Spodumene, this ores you may not remember, but it will be very difficult for you to remember. But if you can remember, it is okay. Even if you don't remember, you should just know certain names and certain idea. That this spodumene, this is a lithium, it contains lithium here. Amblygonite is also lithium, and also aluminum, another metal. So these are all the ores of the lithium that we usually are used to obtain lithium from them. So we extract lithium from them by certain methods. The ores of sodium, and from the sources of sodium from where we get sodium, is the child saltpeter, which is a chemical formula is sodium nitrate. The sodium chloride, we know, NaCl, the salt. So NaCl, sodium sulfate, Na2SO4, which is also a salt. So they are all salt. So the borax, Na2V4O7, the sodium is there, and 10H2, the water of hydration. And the Glauber salt also contains sodium, is formula is Na2SO4, 10H2O. So at least these few names you should understand. Up to borax and Glauber salt, you should remember it as a source of sodium, because it's very easy to remember, and we know because we encounter these salts quite often in our day-to-day chemistry. So the sources of sodium you should at least remember. The potassium, their O's are carnallite, which chemical formula is KCl, MgCl2 6H2O, and feldspar. Feldspar is K2O, so it's an oxide of potassium, and Al2O3 6SiO2. So this is chloride, potassium chloride. So, and here the potassium is found as oxide. Now the rubidium, you see how it looks like. And rubidium, its source is lithium ore. lepidolite, and lepidolite is this one, lepidolite. The lithium, it also contains rubidium, as we saw here. And the triphyllite contains 0.7 to 3% of rubidium oxide, Rab2O. This is rubidium oxide and it's triphyllite, and it contains only 0.7 to 3% of rubidium oxide. So the rubidium is there. The sources of cesium is lepidolite. So as I said, the small amount of sodium, cesium is also there in lepidolite, which is a primary source of lithium. And then pollucite. Pollucite is also, it contains 0.227% cesium oxide. CH2O is the cesium oxide. Why it has cesium has +1 charge, oxygen has 2 minus charge, so this valence here exchange. So CH2O, it's a similar thing we see for the rubidium, or for that matter, all the alkali metals. So lithium, the first element of group 1, exhibits some properties that are different from those of the other members of the group, and this what we see, this is called the diagonal relationship. And its properties resembles, the properties of lithium resembles more to the second element of the second group, but that is the magnesium. So if you look here, lithium, its property more resembles to that of the magnesium. This is because, so that we will see later on why this is. So lithium, it is diagonally opposite to magnesium, and this relationship, the closeness in property is called diagonal relationship. They are diagonally opposite to each other. And so why they are same? Because their electronegativity is quite close to each other, and their charge radius ratio, charge size ratio we also call. So charge to radius ratio is also similar, close. So lithium, it is a very tiny atom, and it's a lithium ion, it's a very tiny ion. And so its size is very small, and it has only one positive charge. If you compare that with the other elements, it is quite, charge size ratio is very high in the case of lithium. And in the case of magnesium, what we see, magnesium is slightly larger than lithium ion, but it has 2 positive charge. So the 2 positive charge divided by a larger size, but we get that charge size ratio is quite closer, and their electronegativity is also quite similar, quite close to each other. So what we get, their property is also quite similar, and this relationship that we get in the periodic table is called the diagonal relationship. So lithium, the first element of group 1, exhibits some properties that are different from those of the other members of the group. Its property resembles to the second element of group 2, and that is the magnesium we have just seen. And this type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. Not only this, they are not only the one pair, there are many other pairs which also show diagonal relationship, like beryllium C, their properties closeness to aluminium. So that is also diagonal relationship. So the diagonal relationship is due to the similarity in ionic size and or charge radius ratio, or charge size ratio, or charge radius ratio of the elements, and the similar electronegativity as well. The monovalent sodium and potassium ions are found in large proportion in biological fluids, and that is what we know. The sodium and potassium ion channels, you might have heard in the biology, sodium potassium channel. So this sodium potassium channels, actually they allow certain elements, certain ions to move through because of the potential gradient. So the channels, ion channels are very, actually they work on certain properties, and they allow certain ions when it is required under certain conditions only to pass through. And so they maintain the osmotic balance of the cell. What is osmosis and what is osmotic pressure, that we have studied in the solution chapter. And if you have not studied, you can see your video, I have explained there. So osmotic balance, you can see the osmotic pressure is associated with that, associated with certain concentrations. So the osmotic pressure of the cells are mostly maintained by the sodium and potassium ions, and this sodium potassium ions, their relative gradient allow, and because their movement allows certain ions to also come and go out of the ion channels. And these ion channels are mostly proteins which are found on the cell membranes. On the cell membranes, the cell do not allow anything to come and go out very easily, because there is certain selectivity. If it will allow anything to go out and in, it will be very difficult, but it may not survive, because any ion, any number of water molecule will go, it will disturb its the natural uh, texture, natural concentration, natural ambience. So what will happen? So the many chemicals are there. So the its chemical properties, chemical reactions that happens inside the cell, because of all the biology at the fundamental levels are is chemistry, so that will be disturbed. So the survival cell will not be will not survive, and if the cells will not survive, no animals will survive, no living form will survive. All the animal, plants, fungus, whatever the five kingdoms that you study. So, so for living forms, recently what I have heard, there are five kingdoms, not only animals and plants. There are monera and fungi, or there are some uh, total five kingdoms that you will see in the biology, particularly elite students. You are from J, you don't have to worry about this. So animals and mm, plant kingdom that we should know, because that we see every day in our life. So animals and plant kingdom that we know for the JEE students particularly. So these ion form. So if there is not ion balance is not there, osmotic balance is not there, so these ion channels will also not work, and so cell will not survive. So these ions perform important biological functions such as maintenance of ion balance, so sodium and potassium ions, and nerve impulse conduction. So they are also used in impulse conduction. Not only they, the magnesium and calcium ions are also used there. So the magnesium and calcium ions. So what is the sodium, magnesium, potassium, calcium? You see, so magnesium, calcium are also involved there. So calcium ions are also involved in our muscle contraction, and so many they are involved. So these ions are very important for the function of our muscles as well. They are also important for the function of, or the transmission of the nerve impulse from one place to the other place, so that the nerve cells will not work if these ions are not there in our body. So we also need these ions as a source. So that is why we need to eat them from outside, because that is the only reason we cannot synthesize them. We get them from the outside, and then we get them from the food, and that is why we need to eat salt. And also the natural sources of food also contains these ions, so we also get them from the natural sources of the food. The extraction of alkali metals, just look at the extraction of alkali metals. So usually what we, the method that we study for the extraction of certain metals, those methods actually fail for the, in the case of alkali metals, because the alkali metals are very reactive, they are electropositive, they can easily be oxidized, so they are very strong reducing agent, because they can reduce, they get oxidized, lose electrons, and those electrons will be used to reduce others. So they are very good reducing agents. So you cannot reduce them. So if the alkali metal is there in the form of metal cation, so you cannot easily reduce it, because it doesn't have that tendency to accept electrons so easily, because those electrons you will take from some other sources, and whatever the source that you take, they will not easily be removing their electrons. So their electron removal tendency or the oxidation tendency, you will see, you have to compare the with the alkali metals in the neutral form, and that usually is not found there, not found that close. So alkali metals cannot be extracted by usual methods that we normally use for the extraction of metals, and this is because alkali metals are a strong reducing agent. As I just explained, they can easily lose electrons, and so they get oxidized, and they can easily reduce other compounds, other substances. They are very, so they are very strong reducing agents. And so reducing agents, so if you want should alkali metal to get extracted, and that is there in the form of the chloride, halide, or oxide, what you see, the metal is there in the form of cation. So that cation has to accept certain electrons to get converted into the metal, pure metal, and that is not very easy. So they cannot be extracted by reduction, because they cannot, metals cannot, cations cannot be easily reduced, those alkali metal cations, because they like, metals like to remove electrons. Even if you do keep certain electron, it will accept, and then the metal will immediately lose its electron, will become again cation. So they can be not be extracted by reduction of their oxides or other compounds. Being highly electropositive in nature, it is not possible to apply the method of displacing them from their salt solution. So displacement reactions we have seen in redox reactions, as for the example, that in the case of Daniel cell, if you look at the zinc replaces copper solution, copper ions from the solution. That not in the Daniel cell. Usually we see when we put them copper sulfate. In the copper sulfate solution, the idea is using the Daniel said the copper sulfate solution. If you put zinc, what we see? We see the zinc will be dissolved, zinc ion will go into the solution, and the copper ions will be deposited. So the copper ion is there. So this is called electroplating or electrodeposition, and this deposition will not happen in the case of alkali metals because alkali metals usually have a stronger tendency to donate electrons than zinc and other most of the metals. So they cannot be used, they cannot, and the displacement and the reaction, the net reaction that is happening when you put zinc rod into the copper sulfate solution is the displacement reaction. So the zinc is replacing the copper from its solution somehow. So that displacement reaction is also not happening there. It will not be facile in this case. So you cannot replace. It means if you have alkali metal salt, its solution, electrolyte solution, if you add certain other metals, and if that metals allow the alkali metals to get deposited, it force alkali metals to get deposited, then we call the displacement reaction, and some other metal will go into the solution to keep the solution electrically neutral, and the electron that it will provide will be taken by the alkali metals, and alkali metal will be deposited or will be precipitated out. That thing is not facile, not feasible, because alkali metals usually have a stronger tendency to donate electrons than any other metals, other group metals. So being highly electropositive in nature, it is not possible to apply the method of displacing them from their salt solution by any other method. The aqueous solutions of their salts cannot be used for extraction by electrolytic method. And electrolytic method is something that I said, the purification that we do of many methods. Some metals are actually extracted by the electrolytic method. So electrolytic method is there. You take an ionic solution of that ion or the metal, you add something and provide electricity. While providing electricity, you are providing electrons, and so with that electron, it would get the electron and get deposited. So that method will also be not used. Why? Because once you provide electricity and these metals are there, and if the water is available, there's salt solution is there. So what is there? The salt solution, aqueous solution of their salts cannot be used for extraction by electrolytic method, because hydrogen ions will be discharged at the cathode. As cathode reduction happens, so what we expect, we use alkali metal cations, that's a solution, aqueous solution. So what we expect, we can do it to expect that the alkali metals will accept electron and they will be deposited at the cathode. But what we see, the H plus ion is also there because in the aqueous solutions, and the hydrogen gas is produced in place of alkali metals being deposited. And thus their aqueous solutions can also not be used in electrolytic methods to extract alkali metals. And so the hydrogen ion is discharged at the cathode instead of an alkali metal ions, as the discharge potential of alkali metals are very high, and this we call the discharge potential. Though there are many different names, so all these things belong to the electron donation tendency of alkali metals. So all these properties, though different names because of the different processes are given, but ultimately it is mostly the electron donation tendency of the alkali metal. So by using mercury as a cathode, alkali metals can be deposited. However, the alkali metals readily combine with the mercury to form amalgam, from which their recovery is difficult. So if you want to extract pure alkali metal, it will be difficult because it will mix with mercury, it will form amalgam, and from there their separation is very difficult. So method that we use for their extraction is the electrolysis of their fused salt. So instead of taking aqueous solution, we take their fused salt. So the solid salt we take, and the solid salt, then we heat it, we make it in the molten state, they make them fuse, they make their liquid, we make their liquids, and that is called the molten state or the fused salt. So pure solid salt can be heated, and so that it will become converted into the liquid, and so that is we call the fused salt, and means the salt in the molten state. Molten state means the liquid state, the same compound in the liquid state. Usually chlorides we use, and generally another metal chloride is added to lower their fusion temperature, because their melting and boiling points are usually very, very high. We have seen it in the ionic when we saw the ionic bonds. their melting point, boiling points are usually high. So we need to provide more and more energy to make them fuse. So we do certain things. We add certain other metal chlorides to decrease their fusion temperature. So they will be fused at lower temperature. They can be melted at lower temperature. So once they are in melted form, so the fused NaCl, what will the fused NaCl? NaCl is nothing but Na plus and Cl minus. Even in the solid state is Na plus and Cl minus. In the crystalline state, and Na plus Cl minus, they arrange in particular orientation to form the lattice, and so they, but their existence is in, they exist there as Na plus and Cl minus. In the molten state, then liquid state, they are also Na plus and Cl minus, and these ions, they can move now. They are liquid, and liquids have mobility. So the electrolysis of this fused salt we can do, and what will we do at anode? The fused salt, there is no other compound. So this fused salt, what will happen at anode? Oxidation will happen. What will be oxidized? So because we want metal to get extracted, deposited at cathode, so the metal will accept electrons, so it will be reduced. So what is there which can oxidize? Is a chlorine. Chlorine, anyway, we know chlorine gas, it's a neutral, electrically neutral, and chlorine gas can have an stable existence. It has. So what will happen? So chloride will move its electron, lose its electron, two electrons. Two chloride will lose two electrons, or one chloride will lose one electrons. And since Cl2 is formed, so we will lose two chlorides, lose two electrons to form Cl2, and these two electrons will be used up by two sodium metals at cathode to form two sodium neutral, which is actually an element, and it will be deposited at the cathode. This is an example. Similar processes are used for the other alkali metals as well. Now coming to the atomic and ionic radii of alkali metals. So alkali metals, the alkali metals have largest atomic and ionic radii than their successive elements of other groups. So when we look, you look at a particular period, that the first member will be alkali metals, then you see there are many other metals in that period, and those, all the metals will belong in the same period, belong to different groups, all the elements. So this is what it refers. So the alkali metals have largest atomic radii in the period. It means it has largest atomic and ionic radii than their successive elements of other groups. So in the same period, whatever the successive elements of the other groups will be there, in comparison to them, the alkali metals, their atomic and ionic radii is largest, and this largest is why? Because the effective nuclear charge is less, and effective nuclear charge is less. Because of that, the outermost shell electron is loosely bound, so it will be at the largest distance. It will be farther from the nucleus, so the atomic radius is high. And so effective nuclear charge is less, even if we remove one electron completely, so whatever the ions will be formed, so it will be smallest. In the case of anion, we know if any element gets electrons, so the effective nuclear charge will be reduced, so that its radius will further increase. So in the case of anions, we see some other trend. So for the cations, when ionic radii, we compare ionic radii of alkali metals, we usually compare with the all the cations. So one can see here the lithium cation is ionic radii 0.6 60 picometer, and then Na plus 95 picometer, potassium 133 picometer, and from here the rubidium 148 picometer. You see the ionic radii is increasing continuously once we go down the group. So this we get the trend. So it not only for the ionic radii, we also get the same trend for the atomic radii. So atomic radii of all the elements, or the atomic radius. So atomic and ionic radii of alkali metals increases down the group. So their atomic and ionic radii increases down the group. Why it increases down the group? Because of the introduction of additional new energy cells. So the progressive, continuously one by one, the one energy levels will be increased. From here to here, one energy level will be increased. Then from here to here, one extra energy level will be added. From here to here, further one extra energy level will be added. So the atomic and ionic radii of alkali metals increases down the group due to progressive addition of new energy cells. The monovalent ion, the M plus that we see in the case of all the alkali metals here, are smaller than their in size than their parent atom, and that we know why monovalent, the cation of alkali metals are smaller in size than the parent atom. This is because with the removal of one electron, we also remove the outermost shell. So their outermost shell is there because it is of the presence of electrons. Once you remove that, you have also removed the shell, and that is why the what is there, only the core electrons, core shells are there. So the ionic radius is smaller than the corresponding atomic radius because we have removed one shell, the outermost shell in that case, while removing one electron. Now looking at the density of the alkali metals, all the alkali metals are light metals. Yes. And why they are light metals? Light, when we are talking about that, we talk about their density. And why? Because the atomic size is very large, and their atomic radius is very large. So they are also light because they'll take larger volume and to contain a fixed amount of mass. So a fixed amount of mass, they will acquire larger volume. So their density is small. So they are lighter element. So all the alkali metals are light metals. So lithium, sodium, potassium had density even less than water. So if sodium, lithium, and potassium, if you put in water, it will actually be floating on the water. Don't do it. It is very dangerous. They vigorously react with water, but just hypothetically, if you get some other compound similar to the mm, uh, density of the water, you will see which do not react with these metals. You will see they will float on that liquid. So low value of density are because these metals have high atomic volume due to the larger atomic size. On moving down the group, the atomic size as well as atomic mass both increases. So as we know, so as we move down the group, atomic size is also increasing and mass is also increasing. However, the increase in mass is dominant over the increase in size. Why? Because as we go down, as we keep increasing the number of cells, what we see actually, then if I am adding 1s, so distance of 1s, if you look at the thickness of 1s, it will be lesser than thickness of 2s subcell. It will be lesser than the thickness of 3s subcell. This will happen for all the subcells because 1s cell, the electron will be maximum electrons will be 2, and the 2s cell electrons, maximum number of electrons will also be 2, and 3s will be 2, and then so on. So what will happen if the cells are farther from the nucleus? So the electron, what will happen if you just go a smaller thickness? What will happen? The volume will be larger because the radius it occupies is larger, and so that their volume is not increasing in the same extent as their mass is increasing. Even the number of cell is in, if the number of cell is increasing, so the increase in size actually decreases as we go down the group. So if you see the difference usually, so this is 35 in this case, it is 38, slightly different, and that is why you see the density of potassium is slightly more than sodium. That is, some exceptions happens, and so you see the difference 132, 148. It is 15 only in the case of ionic radius, but when we talking about the density, we talk about the metals density, not their ions density. So ions density Li plus do not have a separate or independent existence. It is actually Li, we can have LiF, LiCl, some anion will also be there. So we cannot measure the density of an ion. We can only measure the density of the salt or density of a neutral compound, which is an element. So what happens on moving down the group, atomic radius as well as atomic mass both increases, but increase in atomic mass predominant over the increase in atomic size or atomic volume. Therefore, the ratio mass volume, mass divided by volume, so mass divided by volume ratio, which is nothing but density, gradually increases down the group because mass is increasing more than the increase in volume. Both are increasing. So what is the mass divided by ratio will subsequently increase as we go down the group. And so what we see, the trend in density. Density usually increases as we go down the group. However, as I said, we see one exception in the case of sodium to potassium, because we see the increase in size from the sodium to potassium is highest. So we see the density is reduced here. So sodium is slightly denser than the potassium. Otherwise, we see a general common trend there. So lithium 0.5, the sodium 0.972, the rubidium 1.53, cesium 1. Also here also we see certain changes, but so potassium is lighter than sodium. That is here because of its unusually large atomic size. This value I'll check whether it is right or not, and then I'll let you know. So somewhere I have noted it down. I have to check it. I have not paid attention there. So anyway, so usually density decreases. Now this reversal that we see in the sodium and potassium, as we expect the density will increase as we go down the group. The reversal is because it's unusually large atomic size of the potassium. So in solid states, they have body-centered cubic lattice. So all these alkali metals, they form body-centered cubic lattice in the solid state. And the solid state in the pure the crystal, they will form the body-centered cubic lattice. And the ionization, when we look at the ionization energy of alkali metals, so this is the last topic. So the ionization energy of or ionization enthalpy that we talk about, the first ionization energy of alkali metals are the lowest as compared to the other elements in the same period. And why it is lowest? Because electrons are most loosely bound, and electrons are loosely bound. It means they can easily be kicked out, and so the energy required to remove those electrons is very less, and so the ionization potential enthalpy is less for them, and least for them in the period that they belong. And as we move from right in the period, what will happen? The effective nuclear charge will increasing. It will be increasing. So what will happen? We need more and more energy to remove that electrons, because as the effective nuclear charge is increasing, the outermost shell electron will now more tightly bind with the nucleus. So you need to provide more energy to kick them out of the nucleus attraction. So ionization enthalpy usually increases in a period in the periodic properties we have seen. And under the same rule, the alkali metals, they have lowest ionization, first ionization enthalpy in the given period. And why the first ionization enthalpy? Because after the first ionization enthalpy, removal of one electron, there is many things changes. And why many things changes? First of all, you are making a cation. So you are making a cation, and from a cation you want to remove one electron. So from cation, removing one positively charged and removing an electron which is negatively charged will become more difficult further. So usually second ionization enthalpy always increases. The positive value of energy always increases for the any element. So why the first ionization enthalpy is lowest in a period for alkali metals? The reason is the size of alkali metals is largest in their respective period. So the outermost electron experience less force of attraction from the nucleus, and hence can easily be removed. The ionization energy of alkali metals decreases down the group. And why it decreases down the group? This general trend we have also seen in the periodic table. Usually for anything we have seen a general trend, some exceptions sometimes may happen, but usually the ionization enthalpy decreases as we go down in the period. And this is why, because we are increasing the number of cells, and with the increasing number of cells, what we are increasing, the size we are increasing, so effective nuclear charge will also be reduced. And because of that reduction in the effective nuclear charge, what we see, we need to provide less energy to remove that electron, and so the ionization enthalpy decreases down the group. And that is why, so anyway, the value of second ionization energy is greater than the first ionization energy, or ionization enthalpy for the alkali metals is quite greater than that, because as soon as you remove one electron, what the alkali metal gains, but first of all it becomes cationic, so the removal of electron will be difficult. The second reason is if you look at the electronic configuration, electronic configuration of monovalent cation of alkali metals is equivalent to the nearest, it is equivalent to the nearest noble gas. We gets the noble gas electronic configuration, and that electronic configuration is also a very stable electronic configuration. So usually if you remove one electron, so there will be less of it will, to get the octet rule, according to octet rule, or to get the electronic configuration of nearest noble gas, it will require one electron. So it means once one electron is removed, the cation gets the configuration of nearest noble gas, and so the removal of, and that configuration, that configuration is very stable. That electronic configuration means it's very stable, and so removal of the further electron is much difficult. So electropositive character of these metals increases as we move from lithium to cesium. Why electropositive character increases? Because the ionization potential decreases, and the ionization potential decreases, ionization enthalpy decreases, means we need to provide less energy to remove those electrons, one electron, as we go down the group. So the electrons can now more easily be kicked out from the neutral atom, and so the this electropositive character increases, because now to make this metal positive from a neutral element to make it cationic, less energy is required. So the electropositive character is increasing as we go down the group in an alkali metal group on the first group. Due to their strong electropositive character, they emit electrons even when exposed to light, and that is what they know. So electropositive character is high. So why the photoelectric effect? You will particularly study in physics, and some introductory thing is also there in chemistry, the second chapter, when I taught atomic structure, and from the photoelectric effect, some information we got about the radiation. It's a particle nature or something like that. So in a more detail, you will see about the photoelectric effect in your physics class, modern physics. And so electropositive character increases down the group. So the potassium and sodium, they can even emit, they reject their electron by just absorbing certain light of certain frequency, and that frequency that you will see. So the property is responsible for use of cesium and potassium in photoelectric cells. So we use photoelectric cells where sodium and potassium are used. So these cells, the sodium and potassium metals at the surface, and as soon as they get light of a particular frequency or frequency more than that, they immediately the electrons are ejected from the surfaces. So that is why, so they, due to the strong electropositive character, the heavy alkali metals emit electrons even when they are exposed to light, showing the photoelectric effect. Now the rest other things I will teach in the next class.